Thank you, Alfred, and everyone for inviting me here. I was here the first time in 2005. There was the HAO summer school for solar physics. That was my first time here. I think I was here in the last 4 years at least once, mostly teaching at the Heliophysics summer school. And it's always great to be here and meet all of you. So I'm going to talk about my work that probably has been occupying me in the last 5 years or so. I started as a solar physicist. I then became a stellar astrophysicist, and now I'm almost like a planetary atmosphere person. So I was drifted between field, and in recent years, most of my funding and project was dealing with pretty much implementing heliophysics research into the applications of exoplanets. And I will try to give a brief overview about the main reason to do that, and the benefits, and also some of the limitations. This work was supported a lot by the Living, Breathing Planet team that was one of the Nexus team. Nexus is the umbrella initiative for exoplanet research that NASA created a few years ago. And our team was selected as part of the number of teams for the pilot of this program. And it is led by Bill Moore from Hampton University. So let's talk about exoplanets in general. Before Kepler was launched, we knew about few exoplanets, individual planets. Every time we found a new one, there was a number of press releases about it, a whole excitement. Then Kepler came out, and we found that there are thousands of them, and now we know about thousands of exoplanets that exist. And it's even more, we know by now that roughly every star in our galaxy has at least one planet. So our knowledge about our planets exist beyond the solar system is very conclusive. Okay, we know that planets are there. And with the next missions, TESS was launched, and JWST will be launched even later this year. We hope to get even more information about exoplanets and expand our knowledge. But at the same time, the exoplanet research is transitioning from just detections, and we try to move to exoplanet characterization. This is now our goal. It's not only just finding a planet that sits there. We want to learn really more about that planet beyond just the fact that it's there. But because of that, the field of exoplanet has been in a transition for a number of years now, pretty much after Kepler, from being a purely astronomy field, we just try to detect planets, to planetary science, where we start to try to characterize exoplanets. We really need to shift from astronomy view to planetary science. And for that, I think, and this is the main message I try to deliver in my talk, communication between the disciplines, let's say the NASA disciplines, heliophysics, planetary science, astronomy, and even earth science. This communication is extremely important and crucial to really get progress in the field of exoplanet. And the best example, I can think of is Gene Parker, the discoverer of the solar wind. He predicted the solar wind. He didn't discover it, right? But Gene Parker had background in mechanical engineering or engineering. So when he formulated the equations for hydrodynamic escape from the sun, he immediately identified that the equations are identical to the Laval nozzle that described the transition of subsonic flow to supersonic flow. So for him, it was very intuitive what's happening because the equations describe the same thing. It was the same equations. And this means that in the context of my talk, I think heliophysics processes can be extremely important in exoplanet research. It's very important for us, the heliophysicists, to communicate these processes to those who might not know about them in the astronomy community. So this is pretty much my main message. The outline of my talk, I'm going to talk about the definition of exoplanet habitability, which is the main driver for exoplanet research. We want to answer the question, are we alone in the universe? Of course we're not. There are Klingons, right? And then I'm going to discuss the extreme space weather on close an exoplanet. But this is an umbrella name to say what happens to heliophysics when we use very extreme set of parameters. And we expect these extreme parameters to exist when the planets are really close to the star. And these are the planets that we found around M-dwarf stars that we think that might be habitable, but we really need to think about the space environment and their impact on habitability. I'm going to talk about some specific study I did, or calculation I did for upper atmosphere's heating by extreme stellar winds. And I will show my recent work that suggests that we may be able to look at planets or exoplanets in a new way via radio observations. And then I'll finish my talk. Okay, so the definition of the habitable zone is commonly described as pretty much an irradiance problem. We have a lamp, we have an object. If the lamp is stronger or the object is closer, the object receives more light on its surface. That's the definition of the habitable zone, is based on this very simplified assumption, where we require that the temperature at the surface of the body or the planet to be between 0 and 100 degrees Celsius to allow liquid water to exist, because we believe that liquid water are crucial to the formation of life on the Earth. Okay? Keep in mind that in many of these exoplanet research or ideas, we think that things have to happen just like they are on Earth, which is already kind of wrong in my mind. Okay, but let's put it aside. Okay, so we want to have liquid water on the surface, so there's a specific range for a given lamp or distances that the planet has to be in order to be, or to be considered to be habitable. And for different stellar types, brighter or more faint, like M-dwarfs at the bottom, we can have the habitable zone changing in terms of the distance of the planet from the star. In the case of M-dwarfs in particularly, you can see that the habitable zone is compressed to a very narrow region around the star, which is by far closer than the orbit of Mercury in our own solar system. So the habitable zone around M-dwarf stars is extremely close to the star. And this is something to keep in mind. Now, of course, we can have many other factors that can impact the temperature or the surface temperature of the planet. One is atmospheric factors, clouds, albedo, greenhouse gases, all the things that we try to understand here on the Earth because we have the atmosphere. We can have geological factors that, all the interaction between the surface and the oceans and the atmospheres, outgassing, and plate tectonic, which turns to be now accepted to be crucial for habitability because we have to recycle the carbon in the planet, so we have to require plate tectonic as a requirement for the planet to be habitable. In the context of the space environment, this is pretty much where heliophysics came to place. We can have radiation. This is ambient or flaring activity in the UV, X-ray, etc. And we can have the physical interaction of the space environment with the star, with the planet. This is the surrounding plasma that the interplanetary medium is filled with, the solar wind. Yes?
So I assume the focus on M-dwarf stars has to do with the ability to detect the
Yeah, I'll mention that in a second. But yeah,
okay.
you're pretty much right.
Yeah.
So if we think about the Earth, that it sits in the low density, low radiation environment at 1 AU, in the case of M-dwarf star, just like this lady mentioned, the planet has to be really close to the star in order for us to detect it. So that's why everybody is focusing on M-dwarf planets, because these are the only ones we can actually detect with current instrumentations. But if we move this planet very close, the planet will move to much higher density and much higher radiation, also much higher magnetic field. And in analogy, it's like taking the space station and move it to the cloud layer, and we all know that it cannot sustain there for long because of the interaction with the environment around it. So this is pretty much what we think, or the people I work with think that will happen in these closed orbit planets. Just going to be much higher impact by the environment on the body, on the planet. One thing I would like to mention before I move on, because I'm going to discuss it, it's the concept of the Alphin point or Alphin surface. The solar wind, in the case of the sun, is accelerated from subalphinic to superalphinic velocity. And the point where the transition occurs, we call it the Alphin point, where the speed or the velocity of the wind equals the local Alphin speed. And at that point, we call the Alphin speed, or the Alphin point. The sound speed is an analogy to the sound speed. It's the ratio of the magnetic pressure to the density, just like the thermal pressure to the density is the sound speed. It's the fundamental velocity that exists in plasma. And one thing to mention is that the Alphin surface is not uniform. In the case where we're in coronal hole regions, for example, density is lower, the Alphin point will move further out. Where we have the streamers, where the density is higher, the Alphin point will move closer in. The source surface, which is commonly used in solar physics, is a spherical Alphin surface, if you like, because this is the point where the field lines become purely open. And you can think about it as where the dynamic pressure of the wind overcomes the magnetic pressure that wants to hold it. The field lines is being open, and the source surface is the Alphin surface. But we assume it's spherical in many cases, which is obviously not the case in the real sun. So this is the magnetic pressure and the dynamic pressure of the wind.
Ofer?
Yeah.
The Alpine surface is quite far from the sun. So don't the density inhomogeneities kind of smooth out by the time you get 20 radii?
No, it's not uniform.
It's still not uniform.
The density is not uniform. The magnetic field is not uniform. And therefore, the Alphin surface is not uniform. Yeah. So we can imagine that there's an Alphin surface surrounding the star, or the sun in this case, and outside it's a superalphinic plasma. Inside is a subalphinic plasma. And we can imagine a situation where the planet actually resides in this subalphinic wind inside the Alphin surface. And of course, the interaction there will be very different than the case where the planet resides outside in the superalphinic flow, just like the Earth. And if we take a meridional cut on this is a modeling of a stellar wind of an M-dwarf star, the Alphin surface is marked in white. And if you can imagine a circular orbit of a planet, in this case, it might have a transition between the subalphinic and superalphinic surrounding plasma environment. So if it sits in the subalphinic plasma, its magnetic field, or magnetosphere, if you like, will look like that, kind of standing lobes. In this case, they're kind of horizontal. And this is the case that is similar to the case of Io, or the Io Alphin wings that is orbiting the Jovian magnetosphere in a subalphinic plasma. But as the planet will go outside to the superalphinic region, which is pretty narrow in this case, these lobes will be stretched out behind the planet and will form a bow shock. And this is what we have in the Earth case. Okay? Yes, Sarah.
So I don't know if you are familiar with the stereo deep sky analysis that was done in the last year or so by Craig Forrest and others, where they found very, very clumpy structure all the way out to our sun, and argued that in fact it wasn't even a surface but a fractal kind of structure where you'd be constantly dipping in and out from superalphinic to subalphinic.
The whole thing is dynamic.
What would that do to you though if it was really that structure?
Well, it was just but if this structure is small comparing to the magnetosphere, they'll be very localized. Here I'm talking about moving from the whole environment being subalphinic to the whole environment being superalphinic. Now, this orbital motion is very fast for these closing planets. It's 3 days. So within a few hours, you're moving from in and out. And it's pretty much changing completely in a magnetospheric structure. You can think about it, what happens when a CME hits the Earth. You change dramatically, very quickly, the space environment around the Earth, then you get back to what you had before. This is what happens, but this is only due to the orbital motion around. There's no CME here. Okay, so that's the point. The point is that the orbital motion can dramatically change within hours on a regular basis the magnetospheric structure of these planets. If there's a magnetic field, but even if there's not, think about Venus, for example, doing this. there's still going to be dramatic changes in the induced magnetosphere as a result of these changes in the surrounding environment of the plasma. So we can think about possible unique conditions in these situations. First, just like I mentioned before, there might be transition from the super to subalphinic environments. These fast changes can drive currents, because if you change the magnetosphere of the Earth within an hour from being like this, being like that, you can drive very strong currents as a result. dB/dt equal J to some extent. The extreme conditions, so these planets are very close to the planet, so the plasma density is very, very high. So the dynamic pressure of the wind is very high. We need to take that into account. And this is just the ambient state. We don't account for any stellar activity here. Okay? So the stellar activity will just make things worse. There might be a feedback on the stellar corona if the planet resides inside the Alphin point and it has a strong magnetic field. These fields can interact with each other and do things, reconnections, acceleration of particles, etc. Induce stellar activity. There might be direct absorption of the Alphin heating or whatever heating that we have in the corona on the planet. It's just there. And we can have a strong erosion of the planetary atmosphere by the stellar wind in general. So in general, a lot of the work I will show now is pretty much deal with the question, can close-in terrestrial planets sustain an atmosphere for a long time? Okay, so we're talking about terrestrial planets around orbiting M dwarfs and terrestrial planets that we think might have an atmosphere, but what we try to do here is to say, to figure out, can they sustain the atmosphere for a long time? That leaving out the question, how do they form this atmosphere in first place, if that's where they are? Okay, so that's not something we're even looking at. So I'm going to show a number of examples. We start with Proxima Centauri b. Proxima Centauri is our nearest neighboring star. And a few years ago, a terrestrial planet was discovered orbiting our neighboring star. So of course, it's very exciting to look at this planet and see what we can learn about. So what we did is we assume we're taking the Earth and we're just putting it there. Okay, that's our experiment. You can argue that it's completely wrong. It's a valid point, but that's our experiment. We're taking the Earth and we move it to the position of Proxima Centauri b, and we try to get as much as possible the characterization of the parameters of Proxima b and its stellar wind and stellar corona conditions to drive or to estimate what are the conditions around the planet. And based on that, try to estimate the effect. This was published, it was led by Cecilia Garofalo, and it was published in 2017, or 2016, sorry. So what we did, we took a ZDI magnetograms. This is a Zeeman Doppler map that is created by trying to observe the Stokes components of the stellar field. Of course, there's a lot of uncertainties in these kind of maps, but we think it's still better than just using an approximated dipole or some kind of idealized magnetic field. We did not have a magnetogram of Proxima Centauri b, so instead we looked for the star that has a magnetogram and has very close parameters to Proxima b as much as possible. And we found that GJ49 actually has it. And this is the three-dimensional coronal field based on this map. It's pretty much a tilted dipole that is very strong. What we show here is the meridional cuts of the equatorial planes. It's not a meridional cut if it's in the equatorial plane. I just realized that. This is an equatorial plane. And the color contours show the ratio of the dynamic pressure of the wind from the solution normalized to that at 1 AU with the typical solar wind conditions. And you can see that it can be very, very strong, orders of magnitude higher than that at 1 AU, the dynamic pressure that we experience on average with the solar wind. The black circles are estimated orbits of the planet for different inclinations. We have for low inclination, higher inclination. there's some uncertainty there, so we just calculated both. You can see the Alphin surface, again, marked in white. And the top and bottom cases show different scalings of the average magnetic field because of the uncertainty we had in this map. We just tested a stronger field case and a weaker field case just to have some kind of a parametric range in our simulation. This movie shows the evolution of the magnetosphere of the planet as a result of the orbital motion. And again, you can see the dramatic changes within a course of about 3 days that the magnetosphere experienced just as a result of the orbital motion. Okay, it shrinks, it expands, etc. Here we show line plots of the change in this dynamic pressure in the two cases, the stronger one and the weaker one. And I just want to draw your attention that in addition to this very strong dynamic pressure that we have to start with, there's a huge variations over the course of only a few hours. We get 2 or 3 orders of magnitude, even more, of changing in the dynamic pressure only within few hours. Again, think about a CME, that the dynamic pressure of the CME is 4 orders of magnitude stronger and hits the Hertz within the course of 5 hours. That would be a very, very powerful CME that affects the Earth. Here it happens all the time, just due to the orbital motion. Okay, this is something. And we also calculated the prediction for the change in the magnetopause location. And you can see the magnetopause location gets, at some points, almost, or in some specific cases, almost as close to the surface of the planet. So the planet is almost completely exposed to the solar wind to some extent.
So this is Earth's magnetic field strength?
Yes, this is the Earth at that orbit with that star. That's the experiment.
I want to confirm. You
Yeah.
assume a constant, steady wind, right? So like maybe this star has a frequent flares or CMEs, but you don't assume.
No, it's a static solution, and we extract the orbit in that static solution.
Okay.
Okay, so these variations are, it's a static solution which pretty much move the planet around and extract these points to see what's the environment near the planet along this orbit.
So in the real world, maybe there are more small fluctuations caused by frequent flaring, or.
In the real world, maybe. This is additional work that was done on Proxima Centauri. Katie Garcia-Sage from Goddard ran a polar wind model with the same similar experience. It was a polar wind model that was designed for the Earth. They move it closer to the star, increase the UV radiation that enhances photoionization of the atmosphere. And they also realized that there's a huge increase in the amount of mass that is lost for the major ions just as a result of this location change. Again, orders of magnitude higher mass loss rate of these major ions flowing from the Earth. And again, it supports, and Sean Fidong did a similar work. Both concluded that the mass loss rates of the at Proxima Centauri b should be very, very high. And probably the planet will lose its mass over the course of 1 billion years, which is typical lifetime of a planet. And they also scale the mass loss rate with different temperature of the atmospheres, and you can see the mass loss rates in 1 giga-year, pretty much.
So they have knowledge of the atmospheric constituents?
Yes,
Right?
this model includes all the chemistry. It's a very detailed models about escape from the Earth's atmosphere. And it's calibrated for the Earth. It's calibrated for the Earth with actual observations, which is important. Finally, oops, moving the wrong way. Finally, this is a recent discovery, which I believe is still controversial, about a planet orbiting Barnard star. So we did the same experiment. And in the case of Barnard star, it's much further out. So what we found is that the Barnard stars experience pretty much similar conditions to the Earth. It's not dramatically different than the Earth because it's much more far out. And of course, there's a famous TRAPPIST-1 system that are much, much closer than Proxima b to their host star. And we did a similar simulation when we got to the similar conclusion. But I wanted to do something even further. I want to get a feeling about the quantification of the energy that this extreme stellar wind impose on the planet. Okay, we got tentative results that say, yeah, it seems like there is a high mass loss rate and the planets are most likely to lose their atmosphere quickly, but there was nothing, in terms of numbers, we didn't have we didn't have it that. So I wanted to look at the TRAPPIST-1 system and try to get a better number for the amount of energy that is deposited by this extreme stellar wind on a planet that resides really close. So for that, let's look at the ionosphere. The ionosphere is the layer where the currents, the magnetospheric currents are closed. It has a finite conductivity, and the currents are flowing from the magnetosphere. They close down in the ionosphere and they move back. That's our current system. And the currents equal to sigma E, J equals sigma E. This is a simplified Ohm's law. So it depends on this electric field and the conductance. So in order to do that, I adopted a formalism that was introduced by Margaret Kivelson and Aaron Ridley in 2008. They look at the ionosphere. It was in the context of the Earth ionosphere, and they wanted to understand how does the saturation that we observe in the cross-polar cap potential is really, what's the nature of that? So they came up with this formalism. It's kind of a Jackson-like problem. They think about, or let's think about the ionosphere as a conducting sphere that has certain conductivity. And we have an incoming Alphin wave, which is the solar wind. Now, depending on the parameters of this system, some of the wave will be reflected and some of the wave will be transmitted. And the transmitted electric field can give us a hint or can help us to calculate the amount of energy that is deposited from this incoming solar wind or Alphin wave in this formalism. So the electric field is the motion electric field of the solar wind is minus V cross B, and the magnitude is just the magnitude of the two. Let's put aside whether they're perpendicular or not. We're just going to have a factor of 2 or 3, but we try to get an order of magnitude here. The Alphin velocity is just is given by the ratio of the magnetic field and the square root of the density of the solar wind. So these are the solar wind parameters. So if we know them, we can calculate the Alphin speed. And we can calculate an associated Alphin conductance. For the inverse of it is just mu naught times VA. So did you know that mu naught times velocity gives you units of ohms? I know that now. So we have a conductance that is associated with the wind, the incoming wave, and we have a conductance of the ionosphere. And Ridley and Kivelson introduced this ratio to calculate the transmitted electric field based on these ratios. So sigma p is the Peterson conductance. This is the conductance. Okay, so if we have -1, it's the inverse of the conductance. But it depends on sigma p, the Peterson conductance, and the Alphin conductance of the solar wind. And once we calculate this electric field, we can calculate the energy flux by using this relation here. And it depends on the transmitted Alphin wave from the solar wind. So based on the simulations my group did for the TRAPPIST-1 system, we looked at three of the planets, TRAPPIST-1, E, F, and G. That's how they called. Very creative. And we extracted, again, the solar wind or the stellar wind parameters along their orbits. Okay, so we have the velocity, the magnetic field, the density, and this is the Alphin Mach number just for display. But from these, I can calculate the energy flux that is going onto the atmosphere of the planet.
Can I ask a question back
Yeah.
on your formula on the previous slide?
Okay.
I think of Peterson conductance as something that's very much, a collisional plasma concept, and stellar winds and solar wind is very collisionless. And so Is it the
No,
same or
this is the Pedersen conductance in the ionosphere, not in the wind.
in the ionosphere?
Yeah.
And then the alphane is in the
This-
ionosphere also?
no,
or
this
solar
is-
wind?
This
Okay.
is the wind conductance. Yeah, of course, it's collisionless plasma, so
Yeah.
it's a weird thing, but that's how they define it.
So are those fairly comparable then?
It depends, and I'll get to the Pedersen conductance after I finish this part. So just to compare, as for comparison of the energy fluxes, I used Whitley et al. Who calculated the stellar constant on these 3 planets and the UV fluxes. So we have 2 fluxes, energy fluxes that we compare with. One is the total radiance on the planet and just the solar or the stellar light that comes in, and the other one is the UV irradiance or energy flux. So this plot shows 3 things. The top shows the ratio of the energy flux that goes into the planet normalized with the total energy flux that the stellar wind comes with. Okay, so this is the fraction that goes into the planet from the total that we come with. This one is normalization to the stellar constant, and this one to the EUV flux. And this is quite confusing, and this is just the orbit, by the way, I forgot to mention. Okay, let me give you the bottom line of this whole calculation. You can see that for certain conductances of the ionosphere, Pedersen conductances, the energy that is deposited into the atmosphere is almost 1% of the total stellar energy flux that comes. This is a huge amount of energy. That's the bottom line. Now again, it can depend on the angle between the magnetic field and the stellar wind velocity. Okay, you take a factor, you divide it by 2 or 3. It's still very, very large. And this can potentially deposit very, very large heating onto the planet. It will inflate onto the atmosphere. It will inflate it, and all this mass is lost. So again, it's another way to lose mass from the planet. But this is, again, it just gives us a flavor about how much energy this intense stellar wind can potentially deposit onto the planet. Now, of course, this Pedersen conductance is, it's a major factor, and part of the things that the Nexus team I'm part of is focusing on right now is to use self-consistent thermospheric atmospheric models to get a better idea about what the conductances really are based on these extreme stellar parameters. So we use this model to try to calculate conductances and see, are they 1, or the 10, or the 100, or the larger the conductance is, the smaller the energy flux is. Okay, so if the conductance turn out to be very large, that will reduce this effect. But if the conductance is turned out to be 10 or even 100, it's still a significant amount of energy. So the immediate recommendation we got from all this work that I showed you pieces about is that we should take into account the space environment and the extreme stellar wind conditions in habitability. And the main thing we can say is that the Alphin surface should be roughly the inner boundary of the habitable zone. If the planet sits within the Alphin surface, it's very likely that it cannot sustain its atmosphere for a long time, and therefore it's less likely to be habitable. So we kind of recommended, and this is just a plot that shows the kind of averaging distances of the Alphin surface. We recommend that the Alphin surface can be or can serve as an inner boundary for the habitable zone in a planetary system. Okay, so the next thing I would like to talk to you is, this is a new thing I've been working on the last year. Planetary magnetic field seems to be important. People think they're important for anything in the context of habitability. They can protect the atmosphere, even though we have heliophysics evidence that it actually can be the other way around. And it seems like they're a major and crucial thing in understanding planet formation. Magnetic field can tell us about the internal structure of the planet. So magnetic fields are very useful to know. Now, can we observe magnetic fields of exoplanets? Not really. Okay. Can we observe magnetic fields of other stars? A bit. Planets, not really. Not at this point. In a matter of fact, we don't even have a theoretical significant work about what to expect from the magnetic field on these close-in planets. There's almost there's pretty much no work that was done. Should we expect them to be higher than the Earth, weaker than the Earth, as strong as Jupiter? Nobody really looked into that, which is strange because people were working on planetary dynamos. Yeah, Tom.
Well, I mean, you do have some information, and in many of these M-force situations, the tidal forces are such that the planet should be locked into synchronous rotation. So
Yeah, but
you have one piece of information.
But that's exactly what I'm talking about. If you have a tidally locked planet, should that increase or decrease the dynamo?
Or does it make a difference? I mean, does the dynamo just go like the rotation, like the Rossby number, the equivalent?
Are you talking about stellar dynamo or planetary dynamo?
Planetary, they're all the same, right?
No. But the point is that nobody really looked into that.
Yeah.
It's surprising because there are people who work on planetary dynamos, and there's very little work that was done on this kind of questions. So that's my point.
Okay.
We need more work. Okay, so one way to try to get some information about the magnetic field is through indirect observation of this interaction or possible interaction between the star and the planet. If the planet has a magnetic field, but it sits very close to the star, especially if within the Alphin point, we should see some interactions, and potentially we can see some signals about it. And the main signal that people have been looking at, it was pretty much led by Evgenia Shkolnik in a series of papers. They looked at the calcium 2 emission lines, which are chromospheric emissions, and they see they've seen some tiny increase in the signal, and they try to attribute this increase to the orbit of a planet that they knew is there, especially two well-known hot Jupiter systems that were one of the first to be discovered. So the idea is that the planet orbits around the star. We can have magnetic reconnection that accelerates particles. These are streamed back to the chromosphere, create these kind of hotspots that increase or lead to this tiny increase in the chromospheric emissions. And based on these papers, they attributed this increase to the orbital motion of the planet. This is just a cartoon that shows kind of what happened. With infalling material on the chromosphere been kind of heated in a localized manner. I actually ran a simulation of this. Let's try again. No, this one doesn't want to move. I ran a simulation in 2011 where I took a coronal model with a developed coronal corona and wind, and I dump a planet with a magnetic field in it, just move it around, and you can see that, yeah, there is this interaction. The two fields are interacting with each other. We even have some kind of an infalling material event right here, and we calculated that this infalling material has enough energy to generate the observed hotspot. But this is a very tentative simulation. It didn't really provide us any real information about how this thing occurs. Observations of star-planet interaction is still somehow controversial. This is an attempt to observe similar interaction in X-ray, and Miller et al. In 2012 pretty much argued that many of these events that I showed were attributed to star spots, so they weren't really a result of the planet. And this is a very hard observation to do to start with. So it's still not clear whether we can really see these things, whether they are what we think they are in the context of this star-planet interaction. Now, what about the radio observations? Many people have tried to calculate what will be the radio signal if we could observe auroral emissions from the planet. So the idea is the planet has a strong magnetic field. And auroral emissions create or generate radio emissions, and we should be able to see them in principle. But pretty much all these calculations got to the conclusion that the signal is just too weak to observe with anything that we'll have soon in terms of radio observations. And keep in mind, we also have the limitation that we cannot observe anything in the radio under 10 megahertz from the ground, because this is the cutoff frequency for the ionosphere. The ionosphere doesn't allow radio waves below that frequency to go through. So here we're talking about the planet as a radio source. Okay, so it's orbiting around, generates emissions, and we can try to see it. Probably too weak. Now, we came to another idea following a new development of the Batsaras code, which pretty much, I'm just going to move forward. The idea is to take the corona solution and generate synthetic radio emissions. And this tool was developed for solar radio observations, of course. And it calculates the thermal free Bremsstrahlung radio emissions. And we currently try to implement non-thermal emissions as a result of particle acceleration, which is, of course, important. But this tool gave us pretty good agreement in the radio flux up to these frequencies. Here you see this deviation. This is because this is based on a dipole simulation. And all the high frequencies solar radio features come from active regions, which we don't have here. So that's why we have this kind of deviation. But here the model on these radio emissions or radio images do a pretty good job in reproducing the sun. And Sofia Mushko had this paper last year. So I took this tool and I said, okay, let's try to see if we can get the background emissions from the star and then put a planet there and see if we can see the modulation of the planet on the background radio emissions. And the way it works is that the radio array, it's not straight, but it's moving with certain paths based on the density variations from the surface out in the corona. The density variations define the plasma frequency, and the plasma frequency is changing, so we have a certain path of the radio wave. Now, if we put the planet there, the plasma density at that point is changing, so the path of the ray will be changing. And this is, of course, for a given frequency. Okay? So we can construct a model where, again, we have the planet dumped into this coronal solution, and we can put the planet in different locations. We can have the planet with different magnetic fields, and we can try to see if we can actually see the impact on the ambient radio emission that comes from the star. And indeed, we see something. These are the solutions, three-dimensional solutions. You can see the planet at different locations. So we have, the planet is on the left. It's in front of the star. It's transiting on the right, and it's being eclipsed by the star. Okay, so we have the planet is moving around, and this is the associated radio images in two frequencies, 30 and 250 megahertz, and you can see that we see this modulation in the image. Now we can take these images from different angles and integrate the flux in each angle to build a light curve. And this is what we have here. You see the light curves. This is the phase, and this is the light curve for given frequencies. And this is just different cases where the planet is close with weaker and stronger field, and this is when the planet is further out with the field weaker and stronger here. But you can see that, especially in some specific frequencies, we can see the modulations, and they're not really, really tiny.
So BP here is a planetary magnetic.
Yes. So it's pretty much Earth-like field on the left and more like Jupiter field on the right. So 0.3 and 1 Gauss. And this is just an animation that shows the whole thing in motion. Again, we have two cases, a close-in weaker field case and a farther out stronger field case here. And this is just the light curve that we're going to observe. The main findings we have with this experiment is that if we can observe the flux of the star, the radio flux of the star, which is not trivial, it's limited to only very close stars, Proxima b and HD 189 seems like they have actually a quite strong radio emissions. But there are actually a number of even solar-like stars that seems to be pretty bright in the radio. But the idea is that if we can see the ambient radio flux from the star, we should be able to see the modulations. And they're significant. They can be 5 to 10 or even more % modulation in the light curve, or in the total flux. And even more importantly, these modulations could be seen in principle not only in the very low frequencies around 10 megahertz, but even in the 1 gigahertz range. We should still be able to see them according to this experiment. Whoops, sorry, went backwards. Now, of course, non-thermal emissions can just make it even worse. So the fact that we don't have the non-thermal emission here, it's a good thing because the non-thermal emission will just we expect it to make even stronger modulation by the planet. And of course, we need the radio observers to the rescue. This is purely theoretical. And we need radio observers to go and try to look for these kind of things. But we have the tool that we can help to focus the particular frequencies to search. And we have a plan, or we have a proposal to simulate a number of specific systems, like Proxima Centauri and HD 189. So we may be able to help to, again, build a very specific a set of observations. Okay, so let's wrap up. The bottom lines here is that close-in planets, what we call habitable planets around M dwarfs, they experience extreme space weather conditions. And these conditions must be taken into account when we consider habitability of these planets. There's much higher density, a stronger field, and the consequences, a strong Joule heating potentially at the top of the atmosphere, and very high atmospheric loss rate, that potentially these planets can lose their atmospheres very quickly. And it can also become enhanced by these sharp transitions between the sub and superalphanic locations. And we estimated that the Joule heating on these planets can be of the order of 0.1 to 10 watts per meter square. Just for reference, the solar constant is about 3,000 watts per meter square, 3,500. It's not much smaller than the total solar constant we receive on the Earth. It's a lot of energy. And the Alphin surface should be served as an inner boundary to the habitable zone. Of course, we need to define what's the Alphin surface distance for that particular star, but we have the tools to get a pretty good estimation about that. And future studies, we need better definitions of the conductivity of these ionospheres. We run a number of simulations which start to get really interesting situations where the ionosphere is not a thin layer anymore. It's actually a very extended layer, which is different than what we have on the Earth. In general, all these experiments are just really cool plasma physics experiments. Just take things to the extreme and see what happens. Take a Jupiter-sized field and dump it in the core and move it around, right? It's just interesting to learn about. And of course, we need more exact calculations about the atmospheric loss rates, and we need to involve more atmospheric models or upper atmosphere models for that. And we need more information about stellar and planetary fields. And the holy grail is to be able to observe magnetic fields of these planets. And that's it. I'll take your questions.
All right, we have some time for questions. Travis.
So one of the central ideas of the test mission was to find these habitable systems around M dwarfs, since 27 days is enough to probe the habitable zone there, so that JWST could follow up and characterize their atmospheres. And so it sounds like the prediction from this work is that there will be null detections of the atmospheres of any planets around those.
I think the consensus among myself and my astronomy colleagues, not the heliophysics colleagues, is that it's better to focus on K and G stars. We're looking for the Earth, the twin of the Earth. M dwarfs are just too too much things happen there, especially at these close proximities. That it's. But there's the observational constraint that we can only detect these Earth-sized planets near M dwarfs. So.
Well, you can detect the Earth-sized planets around larger stars, but it's harder to characterize their atmospheres because of the
JWST will never be able to characterize the atmosphere of an Earth-sized planet around the M dwarf because it'll be too close. Even with transmission spectroscopy, it'll just be very, very hard. Jupiter-sized planets would be more possible.
No, but HST's done it Jupiter size on a G dwarf, and it's
right.
a scaled down version of that is rocky planet around an M dwarf. It's supposed to be possible. That was one of the justifications.
I'm sorry, it's a direct imaging.
Yeah, direct imaging.
Right, it's the transmission spectroscopy. Yeah, it might be possible.
Well, I'll
if there's
quote,
no atmosphere there to detect, it's not going to be possible.
I think perhaps what we really need is patience. I mean, 95 there were no planets, no exoplanets, right? 95 there, Seinfeld was on. It wasn't that so long ago, and within a decade we just moved to the next level of every star in the galaxy has a planet. So we just need maybe a bit more patience, and it might not be just bigger telescopes. Just we need this technological idea that will really take us to the next level, or some line that somebody will just think about this line that nobody thought about, and suddenly, that's how we find it. So we need patience, and we need better communication again between the systems. I don't think we can look at the universe in an idealized manner when you try to observe the complicated stuff. That's how it is.
Bill.
Yeah, to what extent is the Jovian system itself capable of shedding light already on some of these interactions that you're talking about?
Well, we know about the subalphanic interaction. It's all IO. That's where we know everything about that. The outgassing, Enceladus. It's kind of a mini system of larger systems. So it just adds to my point. We need to use solar system knowledge to expand our knowledge about beyond the solar system research.
But I'm just wondering if you were to take a model that you have, put the Sun over here, Jupiter here, and put Europa or Io or something in there, and just try and simulate that system, given what we know about it, would you end up with something sensible, or would you?
Well, you're talking about modeling issues, like you have to capture everything at the same time. But yeah, in principle, you should be able. I think.
I'm just wondering if it's a useful exercise or not, or if the conditions there are so radically different that you have very different.
Yeah, I think the conditions are different. They're not that extreme as much as the systems I was mentioning.
I have two questions. One is, you assume the magnetic field structure of the photosphere, and most of them are dipole-like in your calculation. How common for such active dipole structure is how common?
I think this is an observational bias that we cannot really observe the small-scale field. So this is pretty much what we see. We sometimes see multiple.
Are there any effects on such small-scale structures for the results?
So we did some experiments in a different context. So my group also studied, especially Cecilia Garoffa was leading that, the effect of complexity on massless rays from stars. And we pretty much took these maps and artificially inject small-scale features. And she was able to develop a scaling law that works really well to predict the rotation rates of different stars, assuming there might be complexity taking place. So yeah, it's important. But here, this is what we have. I mean, I could just take a dipole, right? But I wanted to use some kind of a more realistic, data-driven simulation.
second question is about your radio calculation for Proxima planet final radio modeling prediction of the radio observation of a planet existed. So I'm working on a flare observation of Proxima Centauri using optical and X-ray. And the Proxima Centauri has a frequent flare. And how is the fluctuation in the radio, low frequency radio, to how affect?
How it will affect the modulation or ability to observe it? That's a great question that I don't want to answer. I mean, it's probably going to screw it up, or it's going to make it much harder. But I think so. First, if it's a planet, it should show up in the same place. So if again, just like in the optical transit, also there's variability. So you need to take many orbits to kind of throw away the background. But I think it will be a challenge. But one thing you can probably do, and actually I submitted a proposal about it and I put it there. We can also monitor the X-ray and UV variations or the optical. And so you kind of have some of this background information with other bands. So you can also try to use that to kind of filter it out from the radio. But yeah, it's a challenging thing. This is purely theoretical suggestion. And I'm aware I'm not proposing anything to actually do it. And radio observers should do it, not me.
Ricky.
Yeah, that was my question. I have another one that's just sort of a thought. You mentioned how it's fun to put these experiments together and sort of see what the effects are. Are there any? Do you think there are any parameter regimes where instead of mass loss, there's mass gain in the planet, basically mass transfer from the stellar wind to the planet?
Yeah, probably.
Yeah.
But
could be interesting.
I think the wind is massive enough to erode, but it's not massive enough to really affect the once you get to the lower neutral atmosphere, the density is much higher. So yeah, it's another experience to do. But I think it's it's not the mass transfer from outside in, it's the energy, and I think that's what really matters here. But yeah, in principle, you can have wind captures. I actually had a pretty much similar simulation, but the planet was a white dwarf with a stellar mass, and you really see the wind kind of stellar wind goes up, but falling into the white dwarf. So it might depend on the mass of the planet. Maybe for Jupiter-like size planet, it's more important. Maybe for smaller planets, it's not.
Yeah.
I don't know.
Yep.
Any other questions? No? Let's thank Ofer again.